Hello physics students. So here we are at the end of the gravitation topic. And remember at the start of the topic I said that we could actually split this topic into three parts. In part one we studied the force of gravity pretending that the Earth was flat. In other words, that the force of gravity magnitude did not get weaker the higher something went, and it didn't change direction for horizontal displacement. But that was only true because the objects we studied went a limited range in terms of altitude and displacement horizontally on the scale of the Earth. But for things that went a larger distance compared to the scale of the Earth, we had to then account for the fact that the force of gravity got weaker the further you went out, and also that the direction changed as you went around the Earth. And that was gravitation part two. And that allowed us to then understand circular orbits, things that were in forever free fall, and things that are launched up and never return because they're launched with the greater than what we call the escape speed. So two different kinds of projectile motions we studied then. And then I mentioned briefly that there's a part three, and that's Albert Einstein's beautiful theory in which he proved that that gravitation as a phenomenon is not actually a force. What it is matter warping space and time. And that warp space-time accounts for the projectile motion that we see of circular orbits, things going up, and other kinds of motion that part two could not describe. And it turns out that Albert Einstein was correct. His way of thinking about gravity was the true way. But it's not part of the curriculum. But what I want to do is just talk about some aspects of that part three, particularly when it comes to black holes. What are they? And I just want to briefly touch on what a black hole is and why it forms and why the things are true around it. So I'll be briefly mentioning Albert Einstein's theory because it can only be understood by understanding and applying Albert Einstein's part three of gravitation, his theory, replacing the force of gravity with curved space-time. And so black holes form when stars burn out. So what I want to first talk about is black holes, not when there's a black hole, but when there's a star burning and creating light and heat, like our sun. In the daytime, heat and light come to us. So what we have is the star, and we've got planets orbiting around. I drew this way out of scale. If I had the globe here, like about this, big in size, the globe that I showed you in the previous videos, the size of the sun would be like basically the Palisades Mall, if you wanted to get a rough size of the scale of things. And it would be extremely far away, miles away. So imagine me holding the globe miles away from the Palisades Mall. That's the scale. It wouldn't be this close. But I just drew this because it's going to serve my purposes. Otherwise, things would be too big and too small in the diagram. You wouldn't even see what I was drawing. So you got this star, and the star has gravity pulling the mass of the star inward. Okay, so it's like an attraction on itself. Just like if I take a rock off the Earth and I let it go, falls into the Earth, right? And it comes back in. So the matter of the star is pulling everything inward. Why doesn't the star collapse? Because it has nuclear reactions, kind of almost like, imagine a nuclear bomb exploding outward. Well, the sun is nuclear reactions that are happening, and that creates thermal effects, and the matter gets ejected outward, but the gravity keeps it in. So these two forces are essentially balanced. The force of gravity is balanced by the outward force of the nuclear reactions, so the size of the star is stable. Well, star has limited fuel. Oh, I'm getting ahead of myself. Let me create a pause to allow you to copy this down. Okay, so a star has limited fuel and eventually burns out. Like, for example, our sun is about 4 billion years old, I believe, and it'll last another 4 billion. So it's about halfway through its life. The fuel gets spent. And then so what happens is these outward forces go away. They disappear. And that leaves the gravity forces, so now it's going to collapse inward. So what we're going to do is look at the first case, a small star that dies. the ultimate fate of that star will be that it becomes a white, what we call a white dwarf. So the collapsing happens, you see this star getting smaller, but eventually it's halted. And what halts it? Well, kind of similar to this. If I've got this block of metal and I squeeze it as hard as I can with my hand, why don't I crush the metal? You say, I'm not strong enough. Yeah, but why am I not strong enough? The reason why is because I'm cramming these atoms into each other. And the atoms of the metal have electrons. So imagine my fingertips are like the electrons orbiting around the atom. And so you got two atoms here. I crush them. The electrons here are getting closer together and it causes a repulsion. So I squeeze the metal atoms in a fraction of a, not even a fraction of a millimeter, a tiny bit, and there's more repulsion. They push me out so I can't squeeze it in. And a similar thing happens here. The gravity's pulling in, but what's pushing out is the electrons repelling each other. And so the matter reaches a new stable equilibrium. Notice these forces are equal. So the force of gravity balanced by electron-electron repulsion, new size is stable, but smaller. And the planet around, well, it has the same orbit because if you look, the mass of the star did not change. It just collapsed a little bit inward. The mass of the planet didn't change because it's the same planet. So from that formula, gm1 m2 over r squared, with m1 being the mass of the star, m2 the planet, radius, how far apart they are, nothing changed. The orbit stays the same. All right, let me create a pause and I'll allow you to copy this down. Okay, so what happens in another case? What if it's not a small star, but a large star? Something very dramatic happens. So let me first put the label. Of course, I'm putting dies in quotes because, it's not really a living thing, but, it runs out of fuel. Then a black hole is formed. So let me just explain some things of what happens and then why it's called a black hole. So if we've got enough mass in here, this force of gravity is so large that the electron repulsion is overwhelmed and it's crushed. The matter is crushed inward. Once that happens, there is no stopping it. The matter collapses and collapses and collapses. And we're talking, so imagine the Earth and then, the star like being Palisades Mall. No, even bigger than that. Big, giant stars. So you imagine the Earth's big. So this giant star collapses, 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 and it collapses down to a single point. Maybe I'll draw it a little bit bigger because otherwise you won't see. But it's literally smaller than the head of a pin, the entire star. So that's... I'll put star in quotes because it's not a star anymore, but all the matter's there. And then there's this thing called the event horizon. I'll put R of the EH, event horizon. I'll spell it out later. But before I talk about what's in there, I want to talk about what's going on out here. This is the planet. A lot of people would think, okay, black hole sucks things in. The planet's going to be sucked in. But, oops. Nothing changed in the gravity equation. The mass of the black hole didn't change, the mass of the planet, neither did the distance of separation. So, the planet still orbits. So that's the first point I want to make, is that it's possible things to be orbiting a black hole without getting sucked in. In fact, at the center of our galaxy is a very large black hole, and we're orbiting it. The sun is orbiting it, the Earth's orbiting it, and we don't get sucked in, okay? But what's in here? What's in that black hole? So all the mass, let me just write down what I said already. All the mass of the star collapses to a single dot, which means it has no volume and an infinite density. That point is called a singularity. So that point is called a singularity. And at that point, the curvature that Albert Einstein talked about and defined mathematically is infinite at that point. The curvature of space and time together is infinite. And what that means, it's theorized that that makes it possible from the infinite curved space and time for any trajectory to be possible at that point. And that means any trajectory to any point within our universe. If you hit a wormhole inside of a black hole, it's theorized it's possible to go to any point in our universe or even to another universe, and also to go to any time. People theorize and wonder if it's possible to teleport at the center of a black hole and possible to time travel at the center of a black hole. So these are theories, but the problem is they can never be verified because we can never go into a black hole. Well, you can go in theory, but if something were to be sent into the black hole, like maybe you couldn't live in a black hole. The first thing that would happen is the tidal forces would rip your body apart atom by atom. It'd be a very violent death as you're going in. Why is that the case? Well, you don't have to draw this, but as you're going into the black hole, here's your body. And notice your feet are closer to the black hole than your head. So that means that the force of gravity on the molecules in your feet would be larger than the force of gravity of the molecules that make up your head. And that difference would get larger and larger to the point of like your body being stretched until it starts ripping apart. Okay, so even before you got to the black hole, your body would be dismantled on a molecular level. So it doesn't matter what you send in, solid steel, titanium reinforced, anything going into the black hole is going to get ripped apart. Once it gets to the black hole, it would get, after getting ripped apart, it would get crushed. And there's no atoms possible. Remember, the electron repulsion was overwhelmed so that even the atoms themselves get crushed down to a single point. And if you can't have an atom with carbon, 6 protons and 6 electrons and hydrogen and water, you can't even have those atoms, you can't have human beings. So no living thing could get into a black hole. and exist in that black hole, the atoms themselves would be crushed. So that's one point. So then you might say, well, why don't we just look and see if we could see the wormholes with a telescope? The problem is the gravitation is so intense that even light can't escape. Remember, I was talking about escape speed when we were talking on Earth. If I could throw something up faster than 11,290 meters per second, it would go to outer space and never come back. So if I'm on a less massive planet, like say, or celestial body like the moon, I could throw up something with less than 11,000 and it would escape. But more massive, even more massive than Earth, means the escape speed gets larger and larger. Eventually what happens is there's so much gravity, so much mass inside this black hole that even if you took the lightest thing we know, traveling the fastest that it can go, which is light itself. So imagine a beam of light. You never think of that as something that you could stop. You shine a light, shoo, flies across the room almost instantaneously. That thing that goes so fast with so little mass, so little inertia, if I shine it away from a black hole, within this radius here, the gravity is so intense that it sucks the light back in. So even light can't escape. And that brings us to what we call the event horizon. The event horizon, well, what is that? The event horizon, let's basically split the term up into two words. An event. An event is, well, if I said there's an event, there's the senior prom or whatever. That's not only a particular location, but a particular time. If you show up at the right place, but the wrong day, you're not at the event. If you show up at the right time, but in the wrong location, you're not at the event. So you need both a location and time. So that's an event. A horizon is where, like when you're looking at the ocean and you look at a point in the distance, you cannot see beyond the horizon because of the curvature of the earth. So if there's a ship beyond the horizon, you can't see it. So what an event horizon is, it's a point beyond which you cannot see any events. Because if someone is right here making funny faces at you, the way we would see that in normal situations, light hits my face and then it goes to your eye. And that's how you see me. But if the light hits my face and on the way to your eye, it gets pulled back the opposite way, you cannot see my face. You can't see any light from within this region. It's a pure absence of light because any light that originates beyond this horizon, as it's trying to escape, the gravity sucks it back into the black hole. And when you have no light coming from a particular point, the absence of light is black. So that's why it's a black hole. No light comes. You focus your telescope on it and it's pure blackness. You can't see anything that's happening inside. So the event horizon, you can calculate what it would be for a given star. There's a formula. I'll put REH. So the G is the constant we know. The mass, it's on the front cover of the reference table. The mass is the mass of the black hole that collapsed, or the star that collapses in a black hole. And C is this very special term. It's in physics the speed of light. And you could find it on the front cover of the reference table. I didn't bring my reference table with me, but just if you go to the front cover, it's near the top. You'll see this symbol C, 3 times 10 to the 8th, speed of light. Plug it into the formula, and you could calculate how big of a radius for a particular star where the actual size of that black hole. Okay, now the matter's a tiny dot, but that's the part of the space that's invisible to us because of the black hole. So that's a little bit about black holes. It's just the gravity is so intense it collapses all the matter into a single dot. No light can escape. There's all kinds of interesting things that might be possible in the black hole. Wormholes, time travels, teleportation of matter that are only theorized. And you could read about this and people debating about what's inside of a black hole. But we can never know because no one can go into a black hole and survive. Nothing can go into a black hole and transmit information back out because that information, those electrical signals get sucked back in. And the device, when it goes in, gets ripped apart and then crushed violently. So that's a black hole. Fascinating stuff. I just wanted to give you a little taste of that. If you're interested, you could go online, Google black holes, and you could read for hours and hours about all this fascinating stuff. So that's the end of our gravitation, a little taste of gravitation part 3. I hope you enjoyed the concepts about black holes and a little bit about the calculation. Some homework problems tonight. We'll be practicing this formula, calculating what the event horizon radius would be for different celestial bodies, even though they can't collapse like into a black hole like our Earth. What would it have to collapse into in order to be able to get to that point of collapsing the rest of the way into the black hole? These are just interesting kind of calculations that come up on tonight's homework. So I hope you enjoyed. I'll see you in the next physics video.